One variant for the k-fold cross-validation method, it is called the leave one out cross-validation, and it's basically the same thing, but when k is equal to n, the number of data points. For example, here we have our initial database. We leave just one data point out, right? Let's call it x1. So we're gonna have x1 here for testing and d minus x1 for training. Then we do the same with x2. We leave x2 out and we train with d minus x2, and the same thing until xn, every data point. So it's a very expensive and exhaustive method in where we are n times training different models and testing it in one data point that is being left out. So this is the leave one out cross-validation. After training all these models, in all the iterations of the cross-validation process or leave one out or whatever, if we were to decide what is the model that is going to be used actually in the future in production, we need to choose among all the models or all the alternatives, right? And the natural choice is to choose the model that is being trained with our entire training set, right? Which is different to all the models that we have obtained from all our iterations, right? Because all those models were trained with different pieces of the database, but it is reasonable to assume that the best model is the one that trains with the biggest training set, right? Because it's the most representative thing we can have of the reality of the future cases. So that is the model in general we use in production. Okay, so far, we've been studying different models to come up with two columns, basically. The column of the real value of the class or ground truth and the predicted class, the one that we obtained from cross-validation or holdout or random subsampling or etc., right? So now we are ready to calculate the ROR. Right? So we get all these pieces of real versus predicted column, and then we put them together in two big columns and we need to compare them somehow. A natural thing is we imagine that we go over all the pairs of prediction versus ground truth, and then the good cases are the ones we want and the wrong cases are when the prediction differs from the actual class. The thing is, like, here we have different types of errors. One idea could be just the accuracy. It means, how about just going over all the pairs prediction versus actual value and count all the wrong predictions divided by the total number of cases. That could be an initial idea of an error. For accuracy would be the same, like counting all the correct predictions divided by the total number of cases. That could be the accuracy. But we'll see now that this idea is not good for unbalanced problems. In other words, when the proportion of different classes are different. For example, let's say we have two classes, A and B, and the class A has 80% of the cases in our full training set. So if we have a dummy model that always predicts A, then if we calculate the accuracy, we're gonna get all the A cases correctly predicted, right? Because the model always says A. And given that those are 80% of the cases, we will get all our class A cases correctly classified, right? Because our model always says A. But we're gonna get all the cases in class B wrongly classified, because actually our model never is predicting class B. So the accuracy will be, for 80% of the cases, we got 100% of accuracy, and in 20% of the cases, we got 0% of accuracy. So this is 80% of accuracy. And that actually sounds like a good number, but we know that the model is terrible, right? Because the model is a dummy model that always says A. And this is clearly not what we want in reality. So we must clarify the performance separately, disclosing the results in every class, right? And also, per class, we need to point out what is the type of error. For example, when the model predicts A and the actual class is B, it's not the same as predicting B when the actual class is A. Those are different types of error. Let's say we're in March 2020, right, for example, and saying that a patient does not have COVID when she actually has it is not the same as predicting that she doesn't have COVID when she actually has, right? In the second case, you might tell someone that doesn't have the virus, so this person could start spreading the virus. In the first case, it's a problem, but it's not as bad. You will send home someone for a few days to avoid any potential virus spreading, but it's not as bad as the second case. To come up with something like what we just said, we need to create a matrix called the confusion matrix. And this matrix keeps the counts of all the possible prediction versus real pairs. If we have, for example, here the green column with the model predictions and the red column with the actual class values, and imagine in this example we have 18 cases, right? So how we build the confusion matrix? We have 3 different classes, A, B, and C. In the rows, we're gonna use what the model predicted, and the column indicates the real class or the actual class. For example, in the position AA of the matrix, we're gonna count all the cases where the model predicts A and the actual class is also A. So we count here, we have 2 cases, right? So we annotate the 2 there. Now we need to find the A-B position, okay, here in the matrix. These are all the cases where the classifier predicts A, but the real class was B. So this is one type of error. So we need to count here the pairs A-B, and we have 2, okay? Now for C, we want to count all the cases where the model predicted A, but the real class was C, and it's just one case. Now, when the model predicts B, but the real class was A, is BA, just one case. Here is when the model predicts B and the actual class is B. So here the model did right, and those are 5 cases here, as you can see. Then when the model predicts B and the real class is C, is BC and BC2. And then when the model predicts C, but the real class was A, is 2 cases. Now when the model predicts C, but the real class was B, 1 case. And finally, when the model predicts C and the actual class is C, 2 cases. So as you can see, the diagonal is where we want to be, and it's every time the model did a correct prediction, and any positions out of the diagonal are different types of errors. So this is the famous confusion matrix. And just to double check, you need to make sure that all the numbers sum up to 18, the same number of entries in our total training set. Going more general, right, for a problem with t possible classes, we're going to have t columns, t rows, and the position A sub ij is going to be the number of times the model predicts class I, but the actual class is j. Here are some images of real-life confusion matrices. We have a bunch of classes and many cases, right? And usually we use like heat maps to visualize them. I'm gonna leave the links in the description below.